hear both.
It's an interesting thing of what do you request next? What's the right one?
Can you make sure that we don't get into that scrolling thing?
Let me try it again because at least mine is has no problem. Let me,
You can open it. Doesn't matter.
yeah, that's good.
Oh, this is very good.
Wow, this is
So we
different.
could try to
Let's
download.
just download. Yeah. All right, actually, we can try present.
No, no, but when you present, this thing doesn't work. That's the problem.
Okay,
Just say next slide. No, screw it up.
let's download.
You already downloaded one. Show me. And the problem is that you see it opens it in the browser.
Hmm?
It opens it in the browser again, so you get it. Worst case,
Yeah. Yeah. That's odd. It's
sorry. Can we open it with something else?
yeah, we can do this. We'll
No,
just,
from here it works. It doesn't
right.
work.
We'll just say next slide.
And it screwed up all the layout.
Yeah. Yeah. So this IETF is really proper in terms of sort of stuff. So start. Or separate. If you go, yeah, you just open new. It doesn't work in it now. The thing is completely true. Good afternoon, Rift. We are about to start our session. Please take a seat. Please don't forget to sign the sheets. Otherwise, next time we'll end up in LSR room. So, not well, you are participating in the IETF process, and by doing so, you agree to all the terms and conditions. Oh, now it's working. So agenda for today, we are going to bar the agenda and talk about what's going on in working group. Then Bruno is going to talk about results from the hackathon, which is really good. And then for the next 4 hours, Tony is going to talk about Rift. So milestones. The milestone to adopt the protocol specification document has been met. We've got working group document and great progress. Young model is there, at least initial one. we'll keep working on it as we develop protocol. Obviously, one has to match another. And again, great progress. Documents. So we adopted the initial spec. Now we've got second version of it. There's a lot of changes. When Young model is going to match the spec, obviously it's another candidate for adoption. And there are a number of documents that need to be worked upon. I know there's some initial work done on applicability statement. We need to work on security section and threat analysis. There are 3 individual drafts, one describing access or applicability RIFT to access network, one describing applicability RIFT to beer, and third one has nothing to do with RIFT but has RIFT in it. We've got 3 documents. We've got 2 interim meetings, very, very good meetings, good participation, a lot of discussion and good explanation of state machine. So Tony did really great work on explaining, showing the bugs and really going in depth in the protocol. So very successful. And by the way, you can also download recording. It's available online. So 02 has been posted. Tony's going to talk about it. Hackathon will be described by Bruno. So action items, we really need to continue working on it. We need to create new drafts. We need to align Young model with the protocol spec itself. And Bruno. No, you need to switch.
This is much better. So my name is Bruno Reisman. I'm here to do a readout of the hackathon, the RIFT hackathon that happened last Saturday and Sunday. Next slide, please. So we had 8 people participating. You can see the list here. It was mostly people from vendors. There was 1 person from a cloud content provider. And one thing to point out is that I myself am not affiliated with either a vendor or a content provider or operator. So I don't have any skin in the game, and I try hard to give an objective, unbiased view of what I saw in the hackathon. Next slide. The main thing that happened at the hackathon is that we brought in 2 implementations of RIFT, one from a vendor and one open source implementation, and we tested interoperability between the 2 of them. And we also discussed in great detail the things that we learned as we were implementing these 2 implementations, things that could be clarified in the draft, etc. So I'll first talk about the 2 implementations that we used. Next slide. So the first implementation was an implementation from a network equipment vendor. It was brought in by Tony, who's the architect of this implementation, and he has a team of developers working on it. That implementation is a complete, or at least nearly complete, implementation of the draft as it stands today. So that means all the finite state machines are there for the interfaces, the zero-touch provisioning, the flooding for both IPv4 and IPv6. Despite the fact that it's a vendor implementation, it is freely available for evaluation at that URL. There are a few hoops to jump through to download it, but everybody should be able to get it. I got it within 30 minutes or so after jumping through those hoops. And in the report of the interop, I describe exactly what the right steps are to get it. The implementation runs both on macOS and on Linux, but you only get the binary. You don't get the source code, obviously. One of the nice things about this implementation is that it's not just a single node implementation, but you can simulate a large topology with a very large number of nodes in it. And the way you do that is you write a configuration file in YAML that describes the topology that you want to simulate, and then it simulates that whole network for you. Well, simulate is not exactly the right word. It's the actual code that is running. And that code runs on a regular server. You don't need a physical router to install it on or anything like that. Next slide. So the second, I love it how Chromebooks manage to mangle your slides, even if it's just text. The second implementation was contributed by me. So the history behind it is that I signed up for this Rift hackathon, and Tony sent out an email saying, I think it would be a good idea for people to implement the LiFSM in Python, and then we could see if the FSM is well specified, if we achieve interoperability. And that project ran a little bit away from me, so that starting point turned into an actual implementation of the full Rift protocol. As it stands today, it implements the live finite state machine and only IPv4. But one of the things I'll mention later is that we started work on the ZTP finite state machine as well, and that should be complete very soon. And then the only thing missing is the flooding FSM, and I intend to complete that as well. As I mentioned, it's open source. It's hosted on GitHub. You can go and look at it. If you are inclined to contribute to it, you're welcome. I'll happily entertain pull requests. It is written in Python, not because I thought Python would be the best language for a production implementation of Rift, but because it was a good language to just learn about the state machine, to have a reference implementation, to do interop testing. It's mainly intended as a learning experience. It's not intended as a full Rift implementation that you would run in production on a router. It may be suitable to run on a host to connect to a leaf, but nothing beyond that. And I'll talk about my longer term plans at the end. It can also simulate multiple nodes, and I was very careful to write it in such a way that I could interpret the same topology YAML file that the vendor implementation uses. So the neat thing that enables is you can take a topology file that says you want to run these 20 nodes, and then you mark certain nodes with a special flag, and then one implementation will run one subset of nodes, and the other implementation will run the remaining subset of nodes in the topology, and then you can see if they interoperate with each other. And that's exactly what we did in the interop testing. Next slide. So we got together on Saturday morning, and we spent about 1 hour, Tony spent about 1 hour showing his implementation. This is what it is, this is how you use it, this is how you install it. Then we spent another hour socializing my implementation. This is what it is. This is how you use it. And then we spent the next hour trying interoperability, and within an hour we had an adjacency up, which was the goal for the whole 2 days. And I'll talk about some of the takeaway lessons that we took from that, particularly in the area of model-based encoding. So what we spent the rest of the 2 days on is starting to code up the finite state machine for zero-touch provisioning. We didn't get entirely to a running implementation that we could do interop testing with, but we got pretty close, and I expect to be able to finish that within, at most a few weeks, probably sooner than that. And then Tony and I have been talking about doing an additional hackathon before the next IETF, so that we could test that as well. And if there's any other implementations that want to join in that, we could set up something more formally. Next slide. So here are some of the main takeaways from the hackathon. One was that we achieved the original goal of the hackathon very quickly, within a couple of hours, bringing up the state machine. And I think the two main things, and one thing that you should know is that I had not spoken to Tony before the hackathon. He had not given me an implementation of his code before the hackathon. I literally implemented it from the spec, and we tried interop for the first time at the hackathon and got it working within an hour. And I think there are two big contributing factors, two lessons to be learned from that in terms of how we specify protocols here at the IETF. One is that, as far as I know, this particular specification is one of the first ones, if not the first one, that uses a formal data model for the messages on the wire, right? I'm not talking about a Yang data model for management. I'm talking for the data model of the messages on the wire. Normally, if you read an RFC, you have the traditional ASCII diagram. The first byte is this, the second byte is that, and then you start writing encoders and decoders. So when I was writing this code, I literally copied and pasted the thrift data model from the spec and generated the encoding and decoding messages. And literally within 20 minutes, I was sending messages on the wire. The second thing that came out of this hackathon is, as I was implementing the code, I kept very detailed, and I'm sure Tony would say pedantic, notes of what was not clear in the spec, what could be clarified, or things I thought could be done differently. And I wrote that very detailed report in a Google document so that anyone can not just read it, but also add their own opinion to it. And Tony has already started editing that document to respond to all of the comments that I put in. And it's literally about 50 or 60 comments in there.
The running spec, Tony P, Juniper. I find it an excellent way to develop the spec, those live document. As a collaborator, you know what I mean, right? Effort. So get onto a Google Docs. This is far superior to like sending email, to even hallway discussions, people sending me stuff back and forth. You are on this document, and for the very purpose of actually coalescing a spec, understanding and improvement, I mean, it just takes you to a different level. So that's something for IETF, I think, to learn.
Yeah, the other thing that also...
Bruno, sorry for interrupting you. We forgot to ask for note taker and jabber taker. It's a bit late. Do we have any volunteers? Don't look away. Anyone? Thank you.
To follow up on that comment from Tony, he also gave me access to his private Bitbucket repo where he stores the XML file for his draft. And so, there have been various comments where he said, well, why don't you suggest alternative text? And it's very inefficient to do that by email. It's much more efficient for me to just generate a Git pull request where he can accept it or not accept it. And then you have also proper version control of your specification. Okay, so the third result is that we started coding on the ZTP finite state machine, which is a little bit more complex than the LiFSM, and so we'll probably get a little bit more interesting interop results when we're ready to test that. I actually mixed up two different points. Another outcome of the hackathon was that I wrote up a very detailed report of what we did. And there's a link in there on the second bullet. If you follow that link, you will get everything that you need to be able to reproduce the results of the hackathon. So there's instructions how to download the vendor implementation, how to download the Python implementation, how to configure them, and how to actually get to the same point where we got, which is a three-way adjacency. And then during the actual coding, there were plenty of times where we're just sitting next to each other and asking each other questions. This part isn't clear in the spec, that part isn't clear. It was very interactive, and Tony noted down a lot of comments for the next version of the draft. Next slide. So the lessons learned, for me at least, the three major lessons that I took out of this hackathon were first of all, that model-based protocol encoding really works. It really... there's a couple of dimensions that it helps that I go into more detail in the next slide. Similarly, I didn't mention it here, but having a formal specification of the finite state machine also really helps, especially if you have a framework in your code where you can literally translate the events and the states and the actions into your framework. The second lesson that we took out of this is that multicast, even for linked local multicast, just for the hellos, is extremely platform dependent. A lot of the interop bugs that we had to do with the fact that one piece of code was binding to a different source address than the other piece of code, and the defaults for TTL were different, and the whole code, the code in Linux and Apple and Windows for sockets related to multicast is just extremely finicky and platform dependent. And the third takeaway was that attending a hackathon was very useful. I got a lot out of it, and I think everybody else got a lot out of it as well. Not everybody who was there was coding, and even the people who were not coding got a much deeper understanding of the draft and the protocol by being able to play with a real implementation, especially the fact that you could create these complex multi-node configurations. So I'll double click on the first two lessons learned. Next slide. So as I mentioned, Rift uses Thrift to model the messages on the wire. So there's a data model in the spec. The way that it works is you copy and paste that Thrift data model into your the directory, and then you run a Python compiler to generate the code that takes your local data structures in your program and marshals them, encodes them into messages on the wire, and vice versa. So what do you get out of that? You get two main things out of that. One is it's just less work. You, instead of spending hours and hours or days writing code to parse the fields in a message or to encode messages in the fields in a message, it's just all generated for you, so just faster. But even more important than that is that you have a much greater confidence that the code that is used to decode your messages is actually correct. Okay, if you have implemented a protocol that where you manually wrote the code to read a field, check if the length is correct, then read another field, I will guarantee you that I can construct some message that can crash your code.
Wolfgang Beck, Deutsche Telekom.
Yeah.
SNMP used ASIN1 in a very similar fashion, and there were some high-profile bugs in ASIN1 decoders. So it's a good way to do it, but they're not perfect.
Yes, that's why I said higher confidence, because you can still have bugs in the compiler, which is definitely true. But the good thing about something like Thrift is that it's not just used in the network industry, but it's also very widely used in application layer protocols in the big cloud providers. So it's got maybe a little bit more deployment than something like an ASIN1 compiler. We did run into some interesting limitations or gotchas with Thrift. One of them is related to the fact that Thrift does not have any unsigned integers in its repertoire, only signed integers. So if you read the Rift draft carefully, there are about 20 or 30 places where the draft says, here is an signed 32-bit integer that is supposed to contain an IPv4 address, and then there's a comment next to it. You are supposed, your implementation must interpret this as an unsigned integer. And I'm not going to get into the details, but that led to some crashes in my Python implementation, and it has to do with the fact that Python does not have fixed width integers. They are unbounded in precision. So if you create an integer and if you're used in C or C++ that it rolls over to a negative number when you make it too large, that doesn't happen in a dynamically typed language like Python, and you get encoding errors because your numbers are out of range and the thing crashes. And so I was able to solve that, but it took away a lot of the advantages of auto-generated code because you have to go in and fudge all the fields in exactly the right way, and it's just very yucky. Another thing with Thrift is there are many of these frameworks to encode and decode. There's Thrift, there's protocol buffers, there's ASIN1, there's all kinds of things. Some of them are just encoding and decoding functions. Other ones also have a whole transport framework along with them where you can open a session and provide a service. Now, Thrift is one of those, but we cannot use it because Thrift only runs over TCP and some other transports, but not UDP. So we're only using the encoding and decoding functions, but that's already a huge win. So bottom line, I think it's great. I think more protocols, even routing protocols,
probably the link state guy's heart will go up a little bit, speed up, because we can learn lessons where we were struggling with security on the link states. So we can actually change the way we carry things around in the link state to account for the fact that, certain things are covered by checksum, certain things are changing a lot, certain things are not. And if you think about where the stuff belongs, what has to be covered, how it's structured, we can do a better job, okay? I will not show you the flooding FSM. There is like one change how we host leaves when we miscable the fabric. So that was actually also a very good discussion that fell out of the hackathon. We were, tons of stuff at the hackathon. People started to question stuff I was doing that no one dared. Well, I don't know. When you run the implementation and you see these things popping up, and you have to make it work, and you have sometimes people watching sideways, they didn't even look at it, you start to come up with pretty good comments and ideas. So I show you one of these things that fell out, that will be in the new spec. And then I allure to pretty much the last big problems we are attacking with Rift, which is actually, the longer we talk about the stuff and looked at it, the more fundamental it looks to be caused by the way these claws are being cabled. But I just allure, what we're seeing. I think we have a solution. So that will be in the 0.3, quite an elegant, I think, approach. But that's something that started to emerge. The more we talk to people, the bigger configuration we started to attack. So let's go. Oh, sorry, yeah, I forgot the clicker. So I always work off this little thingy, which I find very readable, right? There's a bunch of things. So I have some leaves at the bottom, couple of nodes, basically 2 2x2 pods, and I have these spines which are fully cabled up. And it's a very simple model to talk about things. I have one prefix on a leaf, and I'm breaking some links, and I have big bandwidth asymmetry. This is not important. I will kind of zoom into this picture every time I talk about it, but it's just a mental model to start on something. Yeah. I can't read that either. All right. Cool. So, yeah, all right. Now see, big font. So this is just a warm-up. So one comment that, for example, that fell out from discussing and people implementing the stuff, I just have too much link state history, right? So what OSPF describes as two-way is the full is really a three-way, and the ISI doesn't really have a three-way. It has a two-way and another piggybacked optional FSM, which kind of runs a three-way, right? So when I was thinking through all the stuff, for me, it was utterly obvious, right? What was the lessons learned? So I built this one-way, two-way, three-way, but doesn't match up any of the methodology what people are using on other protocols. So this shows a three-way exchange just as a warm-up. There's no magic. There's, of course, a lot of additional elements being carried around, but I omit all of the stuff for the sake of brevity. And basically what we do is that we go from a node, and when you talk just yourself, it's a one-way. And you do not mirror any of your neighbor's information. You obviously don't have it, so there's nothing to say. The moment you see something from your neighbor and there is no information about you on it, you go in a two-way. So you know that you talk both ways, but it doesn't mean that you see each other. And there's a lot of subtle gotchas here, like MTU mismatches and so on, which I all gloriously omit, which we learned, with the OSPF and ISI's deployments over this many, many, many years. And the moment you see the packet from your neighbor, you already have enough information to reflect him. So you send, I show it by basically showing this set saying I'm sending no neighbor, and then I send the system ID, which is a 21. So, I will not explain what this is, right? It's a sequence diagram. If you don't know what that is, you're probably in the wrong city, wrong room. So you send basically system ID of your neighbor, plus some clutter again. And the moment I got reflected, it implies he saw me, and I'm seeing him, obviously. He saw me, and we reflected me, and that's what I call three-way. Okay? And that kind of cleans up a lot of the stuff that we were doing over the years. And the FSM, when you zoom in, and that is just a simplified version. So all those things are being pulled out directly from the implementation, and Bruno does the same, right? So all the tables, and Bruno actually went even farther than I went. So he has some formal verification that looks at his output of his FSM and goes and check whether his FSM makes sense or has holes. And you can do all this stuff, and it just makes you work on the relevant stuff. Like I say, I'm not looking at core of my protocol. I only chase logic problems now. I don't do anything else. Everything is formalized. I change the model and then I change logic bugs, and that's it. So there's a lot of stuff that you see now. So there's the one-way, two-way, three-way, all very clean. But there's a lot of stuff flying in between, right? And when you start to go through the spec, lots of the stuff makes kind of sense, right? Like you have valid reflection, neighbor drop reflection. Those are the red type of transitions. The blue ones I'll talk in a second. But then you have things like unacceptable header, hold time expired, right? Because you the 3, you lose enough, you have to bring down the adjacency. This is the stuff that is easily accessible. The blue stuff is the ZTP that starts to come in. And when you start to work on the ZTP, you go like, oh yeah, I mean, that's easy, right? You just bring up three-way and then you ZTP. Well, that's not the case at all, because the ZTP itself starts to influence whether you can bring up an adjacency. Because you have like level dependencies. Where are you in the fabric? So pretty soon you realize your FSM machine is negotiate the ZTP config, which is acceptable to both. You start to extend offer, withdraw offer, you can go at this level and so on. And this thing starts to go into the machine. So people can configure you on a fixed level that immediately has influence on this machine. You may get an offer from a neighbor, you may get a better offer. What also plays in here is whether you derived your level from the offer you got from the guy. You tell him, please do not derive the level because you have to build a split horizon. What I try to visualize is that building ZTP well is not just a bolt-on. Okay, like we find a system ID. To build it really from the bottom well, it starts to affect the protocol from the very bottom. So all these blue transitions is like, whom did I peer to? Is this level acceptable? I have an updated ZTP offer. The ZTP offer from the guy expired and so on. And that goes farther up to the ZTP finite state machine. That is coalescing all that you're seeing around you. It's not particularly magic. Okay, it's just that when you build it, it's really influenced the protocol from the bottom. I mean, people build LLDP, people build spanning trees and so on, right? There's different flavors. But to do the ZTP well is an exercise from the bottom. All right, so you soaked a little bit of that. Shouldn't be any surprises much. If people watch really closely, they'll find one that Bruno found. Not? Okay. So the ZTP all of a sudden, and that is now the part that runs during the building of adjacencies, because the offers you're accepting even before you're three-way. Okay, because that influences what other offer what you're offering to other people and what other offer you're willing to take. And after you have enough offer and you know where are you in the fabric, then you're willing to peer with people. So that will be a simple ZTP exchange. So there are two nodes, 21, 22, something like spine, someone above you. The 111 is you coming up, and it's just one adjacency. Okay, I don't want to say neighbor or interface or anything, because then we get into a little bit of a hairball. So it's just one over one interface, you get in those things, one adjacency. And if you look at 111, I'm starting with a level where my local level is undefined, and I just talk level negotiation for the moment because it's like the most illustrative one. Like, how do I find where I am in the fabric? So if you're even perfunctorily familiar with the Rift spec, you know that you have to nail the super spines. You have to start somewhere, from the bottom, from the top. And one good comment from Bruno was that the spec reads well, but it's very hard to know why, right? It tells you what, but it doesn't necessarily tell you why. And my answer is, okay, I'm not Yakov, okay? But you know what I mean, right? I don't do the read the draft. Yeah, I have been on the taking side enough. But you know, I'm not Clancy, okay? I don't write something, you know, that will hold your breath. It's not light bedside reading. It is bedside reading, but not light. So I do a lot of stuff that fell out from implementation experience, protocol specification, and so on. So why do I nail the top and not the bottom? Both have been tried. For better or for worse, people build fabrics, and actually quite often where the claw depth varies. So you can't nail the bottom. Or if you start from the bottom and you offer it to the top cannot agree where it's at. It's get really complex. Because then the top has to say, yeah, I know, but this other guy told me I have to go even higher, so he has to tell the guy down, and all of a sudden you have these discontinuities all over in the fabric, right? I am 4, but you're really 6 because something funky you cannot know about, and it got ugly. So it was much simpler to everybody agreed that they don't have some funky multi-stage super spines. So it's much easier to nail it that the super spine just percolate down, which led to the interesting problem that you don't know when you leave. And the leave property is often desired. So you don't end up in weird places where, you know, your hosts start to become routers, right? Fabric switches. So the nailing bottom of the fabric is optional, very often desirable. The top has to be done. So it percolates down. And Rift offers a seamless, I can nail a configuration where you are in the fabric, or you can just ZTP it, and you can intermix those modes. So you start here in ZTP mode where 111 is undefined, no level, and whomever it talks to is undefined. Because I don't know, I didn't even see him talking to me. So the spine N21, so let's assume this is the super spine. So someone has a level to start with, right? We are diffusing it down. Starts on the 24 and throws this thing at N111. And it's a one-way packet lie. And offers a 24. Now, N111, actually, if you look at the machine, it's actually a very interesting thing. It leads to this is an invalid header reset on the lie, because he threw a 24 at me. I don't have a level. I don't know where I can actually pair with this guy. I can't decide yet. So the header is not valid. I cannot, based on that, go into 3-state. But what I do is I generate an offer towards the ZTP finite state machine, of which you have one running for all the interfaces. So I say, hey, I have an offer here. And I cannot judge whether the offer actually makes sense, not my problem. Here's the offer for a certain lifetime. So the ZTP 111, it's all completely asynchronous. So the smart people got by now that Rift is written for maximum parallelization degree, which the more people implement that stuff and the more we start to work on the spec, it starts to sink in that building protocol specs that offer maximum degree of parallelization looks quite different than building all the address families that reach into all the address families all the time, which has the advantage of compactness, but it implicitly kills a lot of your parallelization potential. So the ZTP, oh, I have enough time, so I'm a little bit like walking, right? Otherwise you have to constrain me. So it gets this offer and runs computation. And it throws back at this specific interface something saying, okay, the highest available level that I see being offered is 24. Looks good to me, I can work with that. The higher available level systems is 21. So there is a bunch of systems gave me this offer. Because now, you know, once you converge the ZTP up, you don't want it to be fragile. You don't want one guy changing their opinion to flip half your fabric over, because you lose basically connectivity on your fabric. So you have to keep count where you get stuff from and what you negotiated. So you have this stable configuration, one link going down and one switch just flipping, you know, upside down what they think will not flip the whole fabric upside down on you, which is actually very easy to do if you design this kind of stuff poorly, okay? So it says our level we can derive is 23, which is, no, decrement by 1. That's the level we'll be working on now as our derived level or computed level. The language in the glossary is, again, Bruno said, why are all those terms? I said, just follow the spec, right? But I will add some explanation, very terse, again, because otherwise it will become a Tom Clancy novel, which is not what a spec should be. And a very important thing is, I tell this interface, what you send out does not constitute an offer. So that has to sink in. So you have to build a split horizon. Otherwise, you'll get ping-ponging effect all over the place. Bruno, something's on your mind.
I'm sorry to jump in the middle of it, but I'm going to remind me of a quote that I'm going to read for you from also Tony Hoare. And it says, there are two ways of constructing a software design. One is to make it so simple that there are obviously no deficiencies, and another way is to make it so complicated that there are no obvious deficiencies. The first one is more difficult. So my concern is that the draft is very complicated. And
okay.
I'm a little bit afraid that all of these mechanisms do exactly the right thing under the set of assumptions that you hold, which is that it's roughly a clause architecture, but maybe some broken links or maybe some miscabling. But I'm worried that there might be some scenario where I create a circle, for example, where things go haywire. And so at the very least, we need to look very carefully at this protocol and make sure that it's actually correct. And that might be part for the academic community, that might be part for a hackathon, but there's also an opportunity to simplify things where possible.
Yes, and the fear is the projection of seeing the unknown, right? So we had this discussion. First, you can make it simpler, be my guest. All welcome, okay? I didn't see a simpler way. It does not mean there isn't one. The requirements are well specified. This is what the market demands from me, okay? And by all means, implement and hammer the stuff. That's why I put it out. Show me how it breaks. I'm all game. I didn't.
Pascal Hubert, we've been looking at some aspect of that, and one of them was the limits of what you can do with thousand reflection, depending on what you can actually see and what you don't know that exists, but you have no clue that it exists. And so that took us in this direction that you're talking about. And so it's not there in the spec, but we've been looking a lot on how we do disaggregation and this concept of positive, negative. And well, when we have it in the spec, I think those aspects at least will be a lot safer. Right? But yes, I mean,
well, I mean, that's just one, like the most complicated, aspect we're closing right now. But this has been done before. I mean, Roll is doing ZTP. People were doing ZTP before. I mean, this is not excessive. Where stuff starts to stick out is the stuff we're working on right now, which isn't even documented. Flooding has been done. Simple? No. For 30 years, people were hacking flooding, either you learned or didn't. It's the price of entry to the club,
Oh, yeah, Atlas. Yeah, I mean, the ZTP stuff is, you start with some very simple principles, and it just has a few rule set pieces. When you cascade it out into the state machine and so on, then the rest of that, it starts to sound complicated. But if you pull back to the basic reasoning, it's only like 4 or 5 different pieces, and they fall out. It's really an implication process.
Yeah, and I think that ties back to the thing that you already brought up earlier. Those simple principles are not spelled out, right? There's no why in the spec. It just jumps right into the guts of the details without spelling out. This is the principle behind it.
I give the requirements section, and honestly, there is a man in this room who knows whom I'm talking about, right? Right? And one of
I don't think it was on this spec, but it was something else, where I laid out the principles that generate, not this work, but some other work. And the wording was, the man has a PhD, and boy, he's not afraid to show it. So, I mean, I can put a section on epistemology, a distributed system, and we can talk about Shardy algorithms, and red-white markings. I don't think it will buy me a lot of friends here. Okay. From the space I can walk, I let it stand, that I hope without us talking, you implement the ZTP, and we pop up the ZTP and you find 0 defects. And I just let it stand. And if you have, by all means, a scenario that breaks it, super. I will be ecstatic. If you have a much simpler way to do it, I'll be ecstatic. Pascal completely floored my whole flooding reduction. Took you 2 weeks, I think, right? Yeah, took a bit. So I show how, and actually fell out very simple. When I show the state machines and the computation algorithm, it won't. But there I have one picture. Here I have literally the stuff broken down to sequence diagrams, right? Which is all the gory detail, already omitting lots of stuff. It is a meta discussion, matter of style as much as substance.
Tony, I think we don't need a large, long paragraph to explain everything, but it's just somewhere when there is a question raised, in that case, specific to that question or that text somewhere.
So I took a note. So I took a note, but I mean, there was more a meta observation, like it jumps right in the middle of it. So I can, fill in the small places, like why is it starting from the top, right? I can fill it in a few places, but the being able to put the whole world into 3 sentences was never my strength, and I think it is, easier said than done as well.
Pascal, again, for this particular one, when we build Ripple like this, the basic thing which makes it loopless is that you start with something, you can always, the rule is like you pick the highest offer that you get. But once you advertise a certain offer, you can never advertise a lower offer, because that's the distance vector thing. You will loop. But as long as you pick and advertise the highest offer you ever got, and never go the other way, you're loopless. That's simple as that.
Yeah, but let's not start on distributed system, design principles and basing algorithms on Shardy, right? Because we'll be here in 3 days anyway.
A small comment
Dima?
about explaining why. I think it's actually very important, especially for people who will be reading those specs 5 or 10 years later, who missed the initial discussion. But it's probably not a good place to put all that explanation into the draft. So maybe it's better to do some companion document.
Sure, and it is called an academic peer review research paper. And I grew up in this world. It is very unfashionable these days.
Okay, a hive is there. Why not?
Bring me slaves, collaborators, sorry.
I can even volunteer to some degree.
Yes, but I work for someone who wants coin. And I'm running with other people who are willing to go to any extent to hackiness to get there first. Okay.
Luberger, I actually agree with you, Tony. I don't think we should be putting a lot in this document on motivation. It'll explode, or actually in the working group. I shouldn't say in the document. I don't care if it's in the document or not. It's just going to explode the amount of material. It'll lead to endless arguments. I don't see a lot of value here, and we would take away the book that Tony's going to sell next anyway. So, but
we have been through those things, right?
Yeah, quite seriously, we don't typically do that here. Is go down all the level of details. Now, what we do is what was suggested is if you have a specific question about something.
Yeah,
sure,
so
add the clarification in the document.
So that's what I did from Bruno, when he asked me that is that utterly non-obvious why it's being built from the left and not from the right. I said, yeah, I had a sentence.
Yeah, and generally we particularly do that if there's a should or a may. Not that it applies here, but we do a little bit in those cases.
All right.
So
that is already enough.
Ignoring questions is not a good way to dealing, right? I understand, and I know you are busy. But if you get questions, it is expected that you're the best person to answer them.
But
right?
giving me meta comments saying please explain how the whole principle fell out, it's just not helpful.
No, not that kind of comment.
Yeah,
A specific
find
comment.
yourself a prof, show up to the hackathon. Lots of those questions have been, answered. And I love answering them where people actually write code and go like, oops, why is it here? Because then I have a profound discussion. When it dwells to the principle, we start to talk about Shardy algorithms. Those are 400 pages books. Go do your masters in this stuff. And then we have sorry, I don't want to be arrogant, but the business of this thing here is to write a spec that works, deploy it, sell it. Interrupt this bloody thing, right? And this is work which is, look at the standard of the stuff's coming out here at this point in time, calling itself a spec. Okay, but it defeats the purpose of this meeting, doesn't it?
Yes and no. So let's talk about why I made that comment to you long ago. The number of people in this room that probably have something above a bachelor's is probably fairly high. The people who are writing code to implement RIFT-at ISP foo, probably not so much. So the draft has to be written in a way, and like you did a wonderful job in terms of here's a schema, a language actually compiles everything for you, does a lot of the work, bang, done. That's great. When you have things that don't fit into those easy mode things, the motivations have to be clear for common reasons. What is the thing? What is it doing? What does it interact with? Which those things suggest how is it debuggable, both on the wire and in an implementation. If people in this room who are bright people can't figure it out, from an explanation from Dr. Tony P, how is the guy that's the guy that's not so bright going to do that?
Cool. Simple passing bar. There is 4 hours of excessive interim. Not that many people joined. Okay? Please watch those 4 hours. I go in excruciating details, running debugs, showing results, bringing stuff up. Watch it. Note your questions. Let's talk.
Yeah, but get it into the draft. That's what people can see. That's the thing.
If people don't watch the interim, they will not read the draft, or the thing that will come back will be full of clutter. Okay. Right. We'll see where it follows. Right now, I like the Bruno's questions. Our kind of like pepper the draft, where for him it was like why. I know what, but I don't know why, and that's a fair thing. All right. So you fire. Where were we? About in the middle, before the metaphysics angels on the pins and everything broke out, right? So you fire off now a two-way towards the guy because you saw him and you give him the offer 23, but you specifically say it is not an offer because I derived the stuff from you. And that's pretty much the whole magic. You see another spine giving you an offer that goes to the ZTP again. Observe, there is no invalid header reset now because you're 23. So you can talk to him, 23 matches, but you fire off the offer. The computation comes back. Basically, see, I messed it up. This is actually another interface from another spine. So that's another interface to the node 111. But this guy computes now, the offer is still the same. I just have two systems offering it, right? So when one system goes down, I know I still have enough offer. I'm staying at I don't generate spurious events, bring down adjacencies, and so on. And you end up in three-way, being at agreed upon levels with the according, like all the split horizons in place. And that's pretty much, the ZTP. But now that's the warm-up. That's the thing, right? And again, that's already simplified. So you end up like walking three states where you compute certain conditions. You end up holding down because you don't want this thing to flap, especially you don't. So you can either have it to converge initially really fast, or you can have to detect that you lost all your super spine or you have been detached from the fabric and everybody has become undefined. This is counting to infinity the other way. There's only one way you can go fast, distributed algorithms again. So the holding down holds you down coming down, but doesn't hold you down when you come up. More subtle than that. But the holding down is a dampener. So you come up without doing a lot of flapping and redeciding, but it costs you when you come, but it is built for maximum speed for coming up, initial negotiation, but when you're coming down, it will make it much slower. And that's, for example, one practical result. When you play with implementation, lots of assumptions, even understanding, theoretical understanding falls apart. The height of fabrics you can build that way is in a sense limited. So I started with 1,000 and they negotiate up very nicely. But when something fails, it's still all very stable. But then when you want to drain a fabric of all the levels or part of the fabric detaches, you get a lot of back and forwards pinging. Now, and it takes a time of counting down to 0. Is it a problem? I don't know. No, something like 24 or 50 is already a very solid number. So this thing is being fed by a couple of local configurations. This is the blue stuff. The red stuff is actually when you recompute the offer and things change. So you decide I go to other level, or you decide I have a better guy I can now join. He shows up higher up. I'll talk about this problem. Yeah.
Did you consider another alternative that was better on the down to up?
Yeah, but the customers were asking that I plug in the node. I want it as up as fast as possible.
I understand that.
Yeah.
It's the bounce.
It's one sentence in the spec you have to reverse. The trigger is actually, do I have any sudden adjacencies? If I have any sudden adjacencies, I have to hold down. If I don't, I don't.
Understood.
Okay. You understand the distributed algorithm is like two choices, a bifurcation. Your choice can have both. Okay. And the blue one is actually when you ended computing. Sorry, the blue ones when the offers are coming in or you expire them. Because don't forget, the adjacency down, you may use the adjacency down for a trigger, or you may use the timeout on the ZTP. So the ZTP may hold the offer and know how long they're valid, because the adjacency has a keep alive, or the keep alive can say, I went down, withdraw the offer. And the updating client is basically when you, and that's a practical implementation consideration. When you're running now 1,000 adjacencies and you recomputed your result, you need to update those guys. So you need a state which may already have to process states while it is doing its own processing of keeping the clients up to date. So that's in the spec. That's actually a picture that has been dotted straight out of the spec. So Bruno is a big fan of ASCII. So he did a great work. There's also a LAI FSM in ASCII. See, not too many states. And the flooding actually also, 3 states is that's the Goldilocks, I find. So I pack everything about into 3-4 states. The details really in implementation go like, so why so many events? Because this is copy-paste. Pretty much you can drive implementation from it. And that gives you the 1-hour interoperability. That's what it does. Very low risk of people going in weird ways. Good. So now I go to something more conceptual, which is much more fun, right? So I don't know how many people remember the original flat reduction and load balancing. There are the key to reaches. So what I had in, and it's running on a binary package, is something that basically was only concerned about the case where everything was perfectly cabled. So we knew we see the same thing up as we see the same thing down, with some variance, which I will not drill down here. And that is buying you 15 to 30% reduction, okay, which is actually quite good. So Pascal, it took a couple of iterations. It was pretty much his idea. I was just proving him the stuff that he suggested would not work, mostly because that's not how link state protocol works, right? And this is something which on a 5-stage folded up is optimal. So that is the theoretical bound what you can do, pretty much. And when you go recursively and it applies level by level, every 2 level is optimal, but if you go multiple levels, you start to lose optimality, which we frankly don't think matters. So what is this? Obviously, beautiful drawing, right? All right. So that's something where I numbered the superspine, and I just show 3 levels. It's completely sufficient to incorporate what this thing is. The middle level, which is some alphabets and some Greek alphabet, just running out of ideas. which are the leaves. And as you see, the connectivity is arbitrarily broken. And the whole point is to show that it is not sensitive to the cabling. Don't forget, we understand what is north, what is south. That's just rift for you. And I can explain why. Well, I like compass rose. So we see this arbitrary connectivity, and it's written down as a list of neighbors to the right, because that's how we start. So A only connects to 3, 4, B to 1 to 4, C to 1 to 3, D to 1, 2. And the problem you're really solving is that the guys from the bottom are generating things, okay? And they push them up. Now, when they start, they don't have much of a choice. If I'm alpha and I produce a new piece of information, that's my piece of information, I have pushed it to everybody above me. There is no flood reduction I can do. But the layer above me is doing huge amount of replication towards the layer above, because A, B, C, D will all replay the stuff again to everybody else. And at high degrees of connectivity, that starts to lead, nothing wrong with it. It's just the processing goes high degree polynomial on you, okay? Actually more. So practically the implementations start to slow down. And it's what's acceptable for you, right? And practically the implementations start to overrun the queues, where things start to get really ugly. We kind of know about all the stuff in link state, and we can push it up to a certain envelope, but this basically makes the job much, much simpler, and the scaling much, much better. So what you do now, basically your job becomes, as alpha is like, pick from this A to D enough people, you get a double coverage up there. And the double is arbitrary, it's just good, right? One link will not kill you. Then when you beta, you want to do the same job. But now, if alpha, beta, and all those guys pick up all the same guy above them, you will start to generate hotspots, both on nodes and links, and you may be actually far worse off than you were without any flood reduction. It's a surprising effect. So how do we go about this job? I'm practically speaking, I'm speaking from like log deployment implementation experience, you know, no magic. So what we built now from this ABCD, each node, right? Because they see the south node tie of ABCD. They see all the north adjacency. They see all the south neighbor, all the north neighbors, but only the north neighbors matter. So everybody has this, in alpha, beta, delta, gamma, has this A to D matrix with neighbors. That's just included, you know, gradually distributed with the protocol, but not farther layer above. And that's why we cannot build optimal solution with 4 layers. But it's just not worth the information pushing. The BCD will do the same thing, pushing thing above, for the information they got from alpha and for their own information on 1, 2, 3, 4, recursive. So first thing, we build equivalence classes. Now, that's just a fancy word. We just group those things based on something we like, okay? We go like, everybody who has more than 2 adjacencies goes into the first class, people with less adjacencies go into the next class. And you can play all kind of games. How much bandwidth do these links have? Or, you know, if it has one difference, doesn't matter, same equivalence class. That's why I call equivalence classes. They're just equivalent for me. The beauty of the whole algorithm, no synchronization whatsoever. Feel free to implement the stuff in each leaf any way you want. So let's assume everybody implements the same thing. And we end up with these 2 equivalence classes, B, C, A, D. Now, when you look at the next thing to the right, alpha to delta, that gives you the neighbors of the leaves up. So alpha is ABD, because it's so messy, this wiring now with all these broken links, it's kind of simpler to write it down. And beta has kind of same, and gamma is the same, and delta is something else. So now the problem is also, albeit alpha and beta have all the same connectivity, we still don't want them to hit the same guys to create hotspots. So now what do we do with all this stuff? Each of the leaves with this information runs something called Fisher-Yates hash. Simple stuff, I explain. It takes basically its own system ID. It does hash it with the system ID in the equivalence classes, and then sorts it. So what does it mean? When alpha uses the BC, it may end up with the sorting BC and beta with the CB. That's why it's hashiates, right? You hash, and you are in equivalence class, and you make sure that you get entropy now. And you'll see how it falls out. Now, obviously, albeit, you have to, what am I doing here? And then you start to pick out things until you have enough coverage to the layer above. So you take these equivalence classes which have been mis-sorted, and you just start to pick up enough nodes. So alpha will pick up B and A, beta will pick something else, and delta will not even see AD. So it will see B and C. So it will pick B and C because alpha is not even connected to C. So you see out of the equivalence class, each of them will only have a part depending on the connectivity. And what it leads to is that basically you have the perfect mass that you wanted. Everybody will pick a minimum of node to get a double coverage, but a varying set of nodes. And there are variants to it. Okay, like I said, it's very robust in the sense, if you don't run it as a leaf, it doesn't hurt. You run a different algorithm as a leaf, it doesn't hurt. If you implement it really dumb and everybody picks the first one, well, then you'll suffer. And that's pretty much the whole thing. So that made it into the spec, and it described more gory details, but that's conceptually. That's pretty much, that kills the problem. Preconditions, of course, the ordering of the fabric, you have to know what is north, what is south, but it is optimal reduction and balancing at the same time. Questions? Crowd is thinning. Stuff is getting hairer. The rest, I think I all talked about. Yes.
Yeah.
Shoot on.
So it's just on that previous diagram.
I'm sure someone is.
If everything's connected and you just did straight ECMP, would you get the same as the balancing? Is this, in other words, is this because you don't have a uniform connectivity?
No, I've shown the non-uniform connectivity as the worst case, that it still does its job. In a full connectivity, it will do actually the optimal job.
You would end up with two nodes. You would pick random two, basically.
Oh, so you're picking random two as
yes.
That's what you would end up with the algorithm, because you would eliminate everybody till you get two left, which are both full connectivity, and you would get those two random nodes.
Okay. But if you had wider ECMP,
so depends what is the coverage desired. If your connectivity is perfect and you want always make sure that every guy up there gets 2 copies of your information through the 2 different nodes, everybody will pick, each leaf, precise now, will pick a different 2 of the ABCD, and that leads to the load balancing, which is so important.
I want to make sure I understood that last comment correctly. Imagine there's full connectivity. There's no link miscabled. Everything is there.
Mm-hmm.
So that means every alpha would have 4 uplinks.
Yeah.
And delta would have 4 uplinks.
Yeah.
Let's say they're 10 gigabits each. Would they have 20 gigs or 40 gigs available as bisectional bandwidth? If I only pick 2, it seems to me I would lose half of my bandwidth.
It's just flooding. It's just flooding. Oh, no, we do that for forwarding. We'll be in trouble.
okay, that was my misconnect too. Sorry.
Oh, okay. Okay.
Sometimes commenting helps.
That was so sly. All right. So yeah, no, this is purely flooding. This is simply to make flooding scale. So, I mean, that's why I put the binary package. Go play. There is actually a minus small f switch, which switches on flat flooding, be my guest. Because it costs me 1 if to flat flood rift. Alvaro.
Alvaro Rotana speaking as an individual. I'm going to ask a why question. Why? Why do you want 2 and not just 1?
Oh, and why don't you want 3? It all depends on your level of comfort. We're just showing you can do 2 because that's the first comment comes up. If the link breaks before this thing reconverges, I'm losing flooding. That's a really bad
So the
thing.
answer is just so you're more comfortable.
Redundant, yeah. That's normal demand of people. Some people think 3 is the magic number. You know, I refuse to solve the 2.5 problem.
And the main reason I was asking is because there are algorithms and implemented protocols and deployed protocols that do basically the same thing, and they focus on one.
No. Yeah, one is simple, really simple.
Correct.
That's what I'm showing too.
Correct. So to your point, I think before of some things were getting complicated. Other algorithms again that already exist focus on one, and it makes it simple, and it's on protocols that deal with a lot of mobility.
Yes, and we talk about mobility.
So
Yes.
one relay
So
stuff like that.
2 is a good number. So if you do 1 or you do 2 and you do them without balancing in a naive way, you just progressively worsen the situation actually. So the trick with the 2 is they have to all spray at load balance. And I never saw that done before. Like, it's not mine. I'm too dumb. Okay. My version was way simpler.
Pascal, again, don't expect exactly 2, right? I mean, there was a joke about 2.5, which was a joke, but actually you get something like that. You get a little bit more than 2, right? Because you won't find the perfect set of ABC, which will make it so that 1 gets exactly 2. 1 will get at least 2, right? So it might be that 1 gets 2, 3 gets 2, 4 gets 3, and 2 gets 4. Not 4, but.
Yes, I mean, and we talked all kind of
example, it might
stuff,
be
that we maybe should take the southbound links into account. We should take the bandwidth of the links because we carry it on Rift, right? We were talking about all the stuff, but then the question will be why, right? So it can do 2 in a naive way. Why 2? Good question. It's
just play it on this picture, you will see that some of them will get a bit more than 2. They may get 3, right? I have not exactly followed all the possible paths, but some of 1, 2, 3, 4 up there will get 3 copies, not 2. But they will all get at least 2.
Yeah. My question was not why 1 is getting 2 or whatever. The question is why alpha is selecting 2 relays A, B, C, D to flood above. If you're fine with only 1,
it may take many more, depending on the connectivity they could reach, right? And until it covers 1 to 4 twice,
right.
it will keep on peaking.
For the question of everything has full connectivity, everything's connected, why aren't we just selecting 1 relay to forward everything up?
Because one link breakage will basically ruin your day for quite a time. And ruining your day in link state protocols is quite expensive.
Again, there's other ways.
In the algorithm, you can make it a constant that you can just tune, right? It's just you have a magic number.
So don't worry about it. All I was asking is why you chose 2. You feel better with 2?
The people holding the checks went like,
I'm fine with
we're
that.
like 2. 2 is a good number, man. Like we can count that. And the 1 makes everyone nervous, right? Single point of failure. No one sold ever a single point of failure as a feature. Like, we might try. Okay. So good. That trigger discussion, it will sink in. Okay. The salient point is complete synchronization free. No one's exchanging any information whatsoever except the standard what goes with Rift anyway to get the reachability. All right. And it pushed a little bit of algorithmic load on the node, which I didn't like because my stuff was only doing things in Tor and super spines. And my why is a long question again, but I like to push everything up, right? That's where you get the big hunkers with CPU and bandwidth and everything. But this is, in my opinion, acceptable for the properties we got out of it. The rest, I think, would shoot to pieces. So next one. Now there will be why? All fair. So having, of course, chewed a lot with the PGP and traffic engineering and this kind of stuff with people practically, the problem they materialized was really failure triangulation, which we can talk about why Rift is firing up BFT on everything, right? So it exchanges local link discriminators, and then you can fire off BFT. It implicitly configures BFT. And the other one was that they want to steer traffic, but when you boil down whether they really understand what they're doing, like their fat flow and scheduling, what they put, and all the ECMP, it was very entertaining, it got very academic, and it was very hard to find people who actually do it on a large scale, except the top 5. But the top 5 do whatever the top 5 do. So like top 5 are the top 5's market. The other people really, the stuff that they were suffering were 2 problems. One was lag disaggregation. Well, no, opposite. Lag You know what I mean, failures, right? So when you hide things in a lag and you say if 3 of 6 fail, take the lag down, and 2 failed, you still have only like 40 out of 60, while the other link has 60 on the lag, and it leads to problem. So you want to disaggregate the stuff. So that's easily done. And then run micro BFT on it. Actually, it's not even micro BFT. It's true BFT over an L3. And the second one that was hitting them in the guts is when you had north, where bandwidth starts to get fat, when you lose a link there, and the guys from the bottom are happily pumping ECMP, that's when the trouble starts. So, of course, you can roll, the heavy machinery that we also love and enjoy, but unfortunately cheap silicon is unavailable, like FRRing and all kind of MPLSing. Or you can just think about the fact that Rift is loop-free. So I can muck safely where I send the traffic without thinking twice, okay? And I can do it node per node. So now, okay, so what can we do with that? What we can do with that is run some magic that at the end will allow a leaf, and it's again all recursive always, to decide how to weight their ECMP per link without telling anyone farther. Okay, again, loop-free NAS is the precondition for those games. So this is not like LFA, any kind of stuff, any complicated stuff like that. What you basically do is you look at your metric, at your bandwidth going up to the next guy, which you have to just flooded along, right? And you look of what does he have north again? And it isn't perfect, because then you can start to argue about, okay, so how much is really east-west without even hitting north? And you can introduce constants, and you can feed some, loop back where you have some analytic systems, but you can't carry the stuff meaningfully in an IGP. You just don't have the resolution. Plus, you don't want to shake your fabric with, like traffic load updates all the time. So this is coarse, but it made people already exceedingly happy. So who am I to judge? So then what is my bandwidth up to a node, and what does he have up again? You sum the whole thing. You take a log 2, and you look like, does this guy have like twice as much? So you get with something where you basically get the logarithm of 2, which you get like the next possible power of 2. Makes for really, really simple math, a couple of bit flipping. And you see these guys to the power of 7, these guys of power of 6, and these guys power of 5. And you normalize the whole thing over basically CMP weights.
So you're doing statistical multiplexing.
Yeah.
And is there any value in the particular algorithm you picked, or is this just one you chose?
I played with a bunch of things.
Yeah.
I would love better suggestions. What I picked is something which is extremely easy to calculate.
Yep, that's what you want.
Right, of course, right. I mean, I don't want to start to do floating point stuff here.
Yep.
As Tony Lee once said when he saw a floating point in back and format, very loud from the back from the room. What? No, he's not.
No floating point. Understood.
Right. So I try to avoid that stuff because I'm also running on the cheapest gear, right? So what the hell I know that Tor will have an FPU. And I got something where you get 50% imbalance, the staff will flip over like, a third of the traffic to the other guy.
Empirical. Good.
Yes, very empirical, I would say. After having played with a couple of really smart ideas that led to really weird situations, run the binary. The interim has like an example walkthrough, which is this here, right? Something much smarter, I'm all for it. I mean, we could dampen this stuff. We could do all kind of sexy stuff, right?
The problem, it will be good if in this type of algorithm to run it through a lot of different type of traffics.
Yep.
Because this type of algorithm is susceptible to traffic problems.
Yes.
I won't comment how I know this, but it is susceptible to problems.
Yep.
And you will want to run it through those traffic patterns for a particular set of applications so that you don't hit a red zone. I can't tell. I can't not tell.
Look, I fully understand. I assume first that your hashing works, right? If your hashing is biased, sorry, I can help you. You should talk, you probably should change your vendor. Once the hashing is uniform, I always suggest it, unless it's the vendor. No, so if the hashing is uniform, assuming that, whatever I do is better than doing nothing.
That's correct.
Okay? So, see, and since IETF doesn't give me higher bar so far, you know, I'm in business, right? You give me a higher bar, I start to stretch. Whatever this thing does will be better than doing nothing. Unless, you know, it flips completely and on the smallest chain, it becomes too reactive. So hence, I dial down the reactivity quite
Right.
significantly.
And that's all I'm suggesting is from past experiences I won't elucidate on. This particular algorithm needs to have fielding test. It's better than nothing, but it could hit a hot spot.
Beauty of it is I'm a really lazy guy. I built Paxos once in life. I decided I don't want to do it again. None of that stuff needs even standardization. Each leaf doesn't, chooses a different algorithm. There's no synchronization of state whatsoever.
That's right. And if someone gets in the middle of having this and they're in a data center where they find an odd case, they can change to something else easily.
Which I duly not disclosed. The admin weight actually is the highest order bit. So you can always go in with the admin cost and basically pop the stuff out.
Right. It's just one of those operational considerations you might want to save for a hackathon or something like that, or for early deployments to say, if you see this, please change this button.
Right. I need real customer traffic running over the stuff, which I may have, but I may not disclose. You know, I'm a sly guy. All right. Yeah, sure, Barak.
Do you take into account also the downlinks speed or not uplinks?
Yeah, so I'm taking into account what goes up to the guy and then the next level. I'm summing them. Well, this is from the leaf. Oh, okay. If you go up.
Check it afterwards. It's similar to the
good.
previous,
Yeah, I forgot the
comment that I
recursion.
gave you.
Yeah, I forgot the recursion. This is just showing at the leaf. The problem was hitting them was on the leaf. They wanted the servers to start actually understand that I lost a lot of not bound bandwidth. That was what the customer presented me. In the middle, yeah, you have the problem again. If you build even higher level.
No, I mean, there could be failures that are remote to you from uplink perspective.
Yes.
But they will affect your uplink. So
yes, but then I have to start to, yes, we talked about that. Then I have to basically push more and more information node to the south and burden the server with more and more flooding and information.
What might happen in two layers, it doesn't really matter, but in 3 layers, there could be that you compute something on the uplinks that is irrelevant anymore to your destinations.
Correct, yes, I'm fully aware. Yes, I'm fully aware. And it is this famous epistemology, which by now some people got on the Wikipedia. The smarter I want to be in every point in the network, the more information I have to slosh around the network to get the guy, which makes the link state basically less and less scalable. And higher requests on the implementation every time. Right, so choices. This is design. Right? This is not art and the meta level. I can assume everything in perfection. Cool. So now that will probably let at least AC's heart beat faster. I need security. Well, I don't need it. Right? Yeah, I mean, what are you up to? I mean, like dinner, right? So we were struggling with all kind of interesting security implication on link state. And it was a learning curve. And the last one we were closing on the attack vector on ISIS with the lifetimes. We did arguably not such a good job on all the initial exchange, like building adjacencies, right? But I mean, we were always historically stretching as far as the market demanded. So hence TCP, MD5, and so on. So we accrued all the stuff and how these things go, you know, that's what it is. And you have to always keep it, you know, working backwards. Here's a chance we can just clean up the slate. And what I'm thinking about is that will put, I like this UDP. I was thinking to flat over TCP. UDP gives you just insane simplicity and performance. Point. That's why all the point-to-point, you know, all the point-to-point networks that they were building using distribution or whatever these guys were called, everybody's working off UDP, right? And look at Quick, right? Yeah.
Pascal, when we run your bundle on limited machines, we kind of seem all to get like a 8% or 10% loss on UDP. Do you have any explanation why we get these things?
You're running 20 full implementations on like 4 cores. You scale it up, you still see loss. That has.
Is it the core? Is it the queues somewhere which overload? Is it?
Think. Did you see a rate limit on flooding in Rift spec anywhere? No, you didn't. Okay.
I'm asking if I have this loop which pushes 2,000 packets to my queue will overload, right? There is no slow start there.
Well, nothing prevents you from building one.
I'm just asking. I mean, if this 8% loss I'm seeing, is it kind of the indication that this problem exists or not?
It's a control system theory. It's how close to the bleeding edge do you take things? Okay? If you look, if you run a car on a racing track and you're running slightly down the middle, nothing interesting will happen. If you want to go as fast as possible, you will start to hitting the curb. And if you really take it to the stretch, you start to run to the grass. If you're a good driver, you start to understand that the moment you hit the grass is probably the time to take the foot off the pedal. Flooding can be run that way, and performance numbers are insane. Okay, so it's really an implementation choice. If you trickle 1 packet per second, you will never lose anything, I can guarantee you. Under no conditions will Rift lose any packets on the channels. So the flooding implementation is initially not telling you anything about any rate limiting whatsoever. Because we're way out of the curve what we were doing 20 years ago, where this was existential problem, right? So now, however, the security thing is more interesting. So those are implementation techniques that a couple of skillful people in the room here will be nodding their head and having interesting thoughts. So now, I'm sticking the stuff in the UDP, but I have the last object, which I call the serialized Rift object. That's basically what you give to your backend code on the model, and you get this munched up thing. You have absolutely no idea what it is, and you shouldn't. It may be compressed, fields omitted. There's different, options there. You shall not care. Okay. But now you have 2 things. One is the initial handshake. And we know that this thing is...
25 minutes.
No chance, man. You told me I have as much as I want. Okay, I'll be flying. So, open for discussions. Not dinner, but otherwise discussions. So, we're sticking this serialized thing. We don't want to deserialize this stuff. It costs money, right? So, you want to flood this serialized object through as much as you can. That's the flooding problem. And on the initial exchange, we saw a lot of problems. We learned replay attacks and all kind of nasty stuff. So I suggest that you put this thing in an optional security envelope, which has 2 things. One, it has a lie nonce, and people should be familiar. Otherwise, talk to Steve Farrell, and he will bore you to death. He's actually a super entertaining guy. The more he drinks, the more entertaining. So we have to. This is recorded. Yeah, okay. I'm losing jobs by the bucket. Well, that's how I made my career. Why stop? And you have basically a SHA over this whole thing. So I can flip the nonces. We could arguably put the nonces into the lies as well, because we always regenerate the lie with a new nonce. And that basically kills everything, including reply attacks and so on. Of course, we have to reflect the nonces. So I know the guy shows me the nonces that I'm supposed to see. But this is all really well understood state of the art. You don't know what the nonce is?
Do you want me to go someplace else?
No.
I was just going to give you a positive input. By the way, this is pretty much close to what Trill does, and Trill is deployed and secure.
Perfect. I should probably deeply look at it, but the one thing they will not have is the link state element sequence number. Do they?
Remember, Trill is based on ISI.
Oh, Trill, sorry. I thought it was some host thing. Okay, I steal it directly, and I will...
Fine. Don't hide your eyes.
I will
hide your eyes.
explicitly not acknowledge you. Okay. All right. So if they did it, problems understood. The lifetime has to go out, but we have a really cool hack which you don't have. Okay. And the really cool hack, and it's not even written down, and that's why I work with smarter people than me. It's Pascal's idea. Nothing prevents me from sticking on the original link state packet the absolute time when I generated this thing. And that makes for a lot of interesting security considerations. Assuming you have some kinds of synchronized clocks, it's optional, right? And you can say like, you know, but if this thing, look at it, has been generated in the future, you probably have some problem if this is generated 1 year in the future. Or if this thing is 200 years old and the lifetime is, you know, an hour. You can nail a couple of interesting things, and you can go to a customer and say, you run the cheapest NTP dirt, and we just tune this thing to 1 sec, and your security of your link state network just goes up. All right? So this will probably happen in 0.4. Mobility support. 6LoWPAN has been extended by Pascal again. He has all the smart ideas. I just talk well, I think at least. So basically on the prefix, you can stick an optional 2 parts timestamp. The first timestamp is just something which is 802.1, where they had to go down to like microseconds or something, a standardized ISO thingy. And the other one is a transaction ID. It's basically a sequence number bubbling up. And we assume at 200 millisec on the fabric, if you stick those things on, but they're optional, okay? Or you can tune it to be finer. And the 6LoWPAN will do this sequence number. And the combination of both gives you something like under 100 millisecond mobility on the fabric. The trick is that if both guys flood you up, you don't have to wait for the guy where the thing is going to flood you up as well. You can figure out that the guy giving you the newer one is the better one, the thing moved. And it makes for a huge difference in the mobility, which a customer requested to work on that. It fell out relatively simple. All right. Flooding FSM, skip it. So the flooding will start, all the stuff will look much messier. Again, well understood. We did it for 30 years for a living, or lots of us. FSM will actually look relatively simple. Here we're changing the spec. So one of the ZTP problems is that something like this for the edge there is a miscabling. Well, for most people. We can talk about running Rift with this kind of stuff where you hook up shortcut layers like LinkedIn wants to do. It's a very unique demand. It leads to either a lot of bow tie routing on your fabric or leads to a lot of flooding that you have to do again. So what we do is, so far the ZTP was saying like, okay, let me join as high as possible. As Pascal pointed out during the hackathon, if you do that and you have a 4 TORs, and you go up to the super spine, that's probably a really dumb idea. You should probably stick with the 4 guys rather than join to the top. So we had this concept of the highest available level, and that's where you build an adjacency as a leaf, right? Here, maybe we even extended to this normal ZTP negotiation where I go like, look, I have a lot of bandwidth and I have 4 guys, and I have this one guy from the top offering me this thing. I should probably stick with the 4 at the bottom. So that was a very practical output from the hackathon. How am I doing? Real good, right? So the only thing that we're doing now is basically spine planes. There are interesting problems there. We spent 3 months scrapping, rescrapping, wasting a lot of mathematical symbols and pictures. What falls out of that the way you deal with it well, you introduce a negative transitive disaggregation, which means that under certain weird failure conditions in multi-planes, you inject from a superspine saying something, do not go to this prefix through me. And I valiantly oppose that, right? By hook and crook, because I couldn't comprehend that building a positive lookup table is trivial. Basically, my thinking was, we don't have a silicon that does a negative hit. So can't make it work. Building positive tables that way is actually trivial. And it has another nice property that it decides how far transitively the stuff has to sink into the fabric. It may go all the way to the leaf, or it may stop after one level where you say, I have enough information to make sure you're not black holing. So that will come in. So the positive disaggregation stays, because the positive disaggregation is like this very fast reflex arc. It happens immediately a layer above you and never goes more than a layer down. And it fixes one-level breakages. But there are multi-link weird breakages when you run multi-plane designs where you black hole. The positive is not enough, and for that we need the transitive negative, which we'll introduce. I was fighting it valiantly. It is actually much simpler than it sounds. So the stuff will fall out. And you made it. Some of us less, some more bored. Okay. Questions, or we already kind of like ran through the whole lot? 06 implementation is out. I was doing a lot of housekeeping. 07 will have the new flooding reduction and mobility. And then the 08 will probably have the negative disaggregation and everything, which allows you fabric any size. And then, frankly, I'm pretty much done, because I think PGP we're thinking to make it optional. Just not enough demand and a lot of complex stuff. All right.
Maybe you already said this, but will then the negative stuff that you just described be in the 03 draft or the 04 draft?
We're aiming for 03. We're aiming at 03, but we already chop up the work. We have discussion about yet a different idea, which I'm always love to. We get probably pull more authors. Here are the culprits who actually caused the problem, so they may as well fix it. But they're willing to contribute, yeah.
When do you want to publish those three? That's basically that, right? I mean, because it's August and some people are French in this room.
Yeah, right. No, that computes how. No, look, at this point in time, people cannot absorb the stuff as fast as it goes out. I tell you frankly. You know, I'm throwing code out faster than people can actually absorb, play with it, and give me feedback. Because so I'm completely comfortable.
There are those two things, right?
Yeah.
One is the partition spine, then all those things discussion, and the other one is just the simple arithmetics of doing the negative in distance vector, which is like 10 lines of text, which I could write in an email. So it just explain how it works is very easy, but the whole story with that in the middle of it is much longer.
Okay, so the whole story is like this. We could, if we put it without a transitive negative disaggregation, it satisfies 95+% of the market. Okay, it's that simple. If people run a simple plain super spine, they don't even need it except really weird cases.
It's probably better to push out 2 drafts quickly rather than one slowly.
The problem is, so that's your point. Well, but there's not much addition behind beside this transitive on the 03. The 03 is the V6 oddities that you saw, where I decided to describe. It should be obvious when you implement it, but I decided to
You
describe.
could finish tete-a-tete, right?
Sorry?
Just two of you talking.
They lost power. They can give me, like when the soccer, they give you another 10 minutes.
So the link to the GitHub with the code is on the slide. If you're interested in looking, writing.
Ignore Jeff, there are more questions.
And Bitbucket link as well.
Sorry?
Yeah, so feedback as well.
Bitbucket for 03 as well.
Sure, I have a special problem on Bitbucket. I can only join like 5 people. Yeah, so I probably make it completely open and available, the Bitbucket. I can just make an open repo. I probably do that because right now it's a closed author list.
Yeah. Or just put it on the GitHub along with Python.
Yeah, sure, but I mean, expect to be heard, right? Because the stuff is now, that is, churning all the time. Sorry?
Instead of flux, changing.
Yeah, of course. Yeah.
Question about negative disaggregation. Did you think about combining negative disaggregation?
Let's go together. It's Thursday. There's no more days. It's always fun. And worst case, you'll just go here somewhere else. No, we need to give it to. Thank you. It's been a pleasure. Thank you.